So our first application of integration is going to be area between curves. This is pretty straightforward. Really, if you just look at it visually, let's say I have some function, this is f of x here, and I have some function g of x here underneath, and let's say I'm interested, say, in the area here, this area that's below f of x and above g of x. So you can certainly imagine, I clearly can't draw a straight line today, but whatever. You can certainly imagine that what we can just do is take the whole area under f of x and subtract the whole area under g of x. And that's exactly what we want to do. We're going to take the integral of f of x minus g of x, but just to be sure, you can think about this also as the upper curve minus the lower curve. You can think about it that way. It turns out, of course, in my picture, which I'm now going to erase because it irritates me that my line goes down like this, they don't have to both be above the axis. It could be something like this, okay? And it still works out. They do a long thing in your book about this. I'm not going to go through it with Riemann sums or anything. I'm just going to point out, if you think about this, like say this is my upper one, f of x, and this is my lower one. Where it's beneath the curve, that second part of the integral is going to be a negative area, but you're subtracting it. So it ends up being positive. So I end up with in this kind of situation where one is underneath and one is above, I basically end up adding this piece and that piece with my approximating rectangle. So it doesn't make a difference whether it's above or below the axis. You are still, in order to get the area between the curves, you want to get the upper curve minus the lower curve. Okay? That didn't come out very well, but you get the idea. In any case, the only difficulty is figuring out which is the upper and which is the lower. Another thing, so you can do that with a picture. That's what I usually do. I just draw a picture. What was the last thing? There was one other thing. Oh, yes. This area between curves is always going to be positive for this reason that I just said, right? Because taking a bigger one minus a smaller one, if it's down here, so area between curves is always positive. In contrast to if I just take the area under a curve, or the area between the curve and the x-axis, if it's down here, it's going to be assigned area, it's going to be negative. Because of the fact that I'm taking one minus the other, my area between curves should be always positive. Typically, if you get a negative answer, it means you set something up wrong. So that's a good check, right, that you actually get a positive answer for these kinds of problems. So let me do a quick example. Or maybe not such a quick example. It's going to find the area between the curves. What was this? Y equals 12 minus x squared and y equals x squared minus 6. Okay, so I'm just going to draw this. You can see these are going to be two parabolas, right? And because it's 12 and 6, I'm just going to do, this is 6, this is 6, this is 12, so kind of so that's my scale, more or less. Okay, 12 minus x squared, that's just going down. and then x squared minus 6 is going up. So this region looks like this. I want the area between the two curves, meaning I want this bit here. That's what they're asking. Okay? So it is some region. So we see clearly when we drew it that this is the upper curve and this is the lower curve. So I know that my area integral is going to be the integral of 12 minus x squared minus x squared minus 6 dx. Notice I am careful to put in the parentheses here so I don't mess up my negative and give no answer. I still have to figure out, though, what my limits of integration are. So basically, I need to figure out what these points are, because I don't know what that x is. So I have to figure out where these two curves intersect. Luckily, that's not too hard. I'm just going to call them equal to each other. So 18. Oh. Yeah, okay, there we go. I'm like, wait, what? X squared equals 9, so x equals plus or minus 3. Okay, so I actually at this point have two options. I can just do it from minus 3 to 3. Or, because of what we mentioned in the last video, that this is symmetric. Okay, it looks a little wonky because it didn't draw it very well, but it is in fact symmetric, right? Both of these are even functions. I can make this 2 times the area from 0 to 3. And it really doesn't matter which one I use. It's just not very, in this case, I didn't make my life that much easier. Sometimes it does make our lives easier to use symmetry. In this case, it's a pretty simple integral. It's not really a big deal. Okay, so let's go ahead and do this integral. I'm going to clean it up. 12 plus 6, 18, and then minus 2x squared. So this is 18x minus 2/3 x cubed from 0 to 3. So what do I have here? 18 times 3. This is 3 times 9, so there's cancel. 18 times 3 minus 8. I think that's right? Because this is plus, so yeah, okay. Fine. Where am I? 2 times 18, 2 times 2. The 18 is 36, right? So that gives me 72. All right. There we are. So there we have. Okay, so there you go. Straightforward, fairly. Okay. So really, as I said, the only thing that we need to do for a problem like this is sort of figure out where's the top and where's the bottom and that sort of thing. All right, let me do another one where this is maybe not as clear. Or we have to do a little bit more. If I want the area between the curves y equals cosine x, y equals 1 minus cosine x, and x goes between 0 and pi. Okay, so they gave you this, so you know that those are the final limits for the area that you want to find out. But let's see what this looks like when we draw it. So here's 1, and let's see pi over 2 and pi. So here's 1, here's negative 1. So this is what? It's not the prettiest. But there's y equals cosine x, right? Now, if I do 1 minus cosine x, so here's my cosine x, minus cosine x is flipped, and then add 1, it goes up to here. So in fact, this is going to look like this. Okay, so you can just plug that into some sort of graphing thing if you want. But they said that they wanted it from 0 to pi, so that means I need all of this area and all of this area. So in order to do this, I actually have to break up my integral into 2 different regions, because you see in the very first part, this is cosine of x. That's the one that's on the top. But in the second part, we have this y equals 1 minus cosine x is the one that's on the top. So you don't really have to call them 2 separate regions, but just so you know, that's what I'm going to do. So if I do area of 1 plus area of 2, you know what? Let me move that over so I have a little more space. So in the first region, I've got my top function is cosine x, and my bottom function is 1 minus cosine x. And then my second region, I still have to figure out the point of intersection, but I'm just setting up the integral first, and then I'm going to go do that. I am out of board space. dx. It's stuffed in there. It really is. Okay. So now let's figure out this point of intersection. Where do the curves cross? I end up with 2 cosine x equals 1. Cosine x equals 1/2. Okay, so that would be this guy. That's going to be pi over 3. And of course, I'm only interested in the intersection point between 0 and pi, so I don't care about any of the other ones. Right? And actually that makes sense. Graphically, that looks about right. So my first integral is from 0 to pi over 3. And then my second region now is pi over 3 to pi. And I had to split it up into 2 because on different parts of my graph, the top function was a different function. Okay, so let's just barrel through this. It's not too bad. This first one is 2 cosine x minus 1. And then the second one is going to be 1 minus 2 cosine x. Okay, so derivative of sine is cosine. This is this. Plus this one is going to be x minus 2 sine x. Evaluated from pi over 3 to pi. Be careful, right, because you've got 2 separate integrals and they're being evaluated in separate regions. So this first one, these guys go to this. The second one, these guys go to that. I plug all this in. 2 times sine pi over 3 minus pi over 3 minus 0 plus 0 plus pi minus 2 sine pi. Oh, that's just 0 anyway. Minus pi over 3 plus 2 sine pi over 3. So so sine pi over 3 is root 3 over 2, right? So this is root 3 square root of 3. So square root of 3 minus, okay, plus pi minus, so I got, wait, root 3 over 2, but there's 2 of them, right? So it's 2 root 3 minus plus pi over 3. Anyway, that's what you got. Yeah, that's what I got. Okay. So, sorry my answer is down here in the corner. It's kind of hard to see. But, yeah. The important thing, of course, is that you get the region right. And very much it's the graph that helps.